Good evening, everyone, and welcome to UCLA. My name is Jean-Luc Margot. I'm the current chair of the Department of Earth, Planetary, and Space Sciences. I want to talk about our mission, which is understand and protect our home in the universe. And I'm thrilled that so many of you are here today, this evening, to celebrate our distinguished alumna and to hear about the amazing story of Cassini at Saturn. We're very excited about this evening's event because it celebrates the accomplishment of one of our alumni. And one of our greatest satisfactions as instructors and professors at UCLA is to see our students go into the world and change the world. Today's students are tomorrow's leaders and innovators. So if you go to the alumni section of our website, you will see the list of professional outcomes of our alumni. And I'm always impressed to see the range, the variety of interesting careers of our alumni. Many of them become involved in NASA missions, but many of them pursue other careers in academia or public service or industry. We're also very excited about this evening's public talk because it is very much aligned with our mission. And we care very much about education and public outreach. And in the past year, our department has touched about 20,000 curious minds, and we're trying to increase that number. Most of our outreach efforts are conducted by our graduate students, and many of them are in the audience today, so I encourage you to talk to them, figure out what drives them, what they're passionate about, and what it's like to study Earth, planetary, and space sciences at UCLA. While I'm talking about outreach, our next big outreach event is the Exploring Your Universe Science Festival. It's an annual science festival that draws thousands of people to campus. And we're very excited to co-sponsor the Science Festival. We have been since the beginning in 2009. So November 5th, appropriate for all ages, lots of demos. We'll have 14 different exhibits just in our department alone, but other departments are involved in the physical sciences and life sciences. So come back, it'll be fun. I'd like to spend a few moments to tell you about our graduate program. Our department is about 70 graduate students, and they're training to become professional scientists. And it's a challenging program that requires serious commitment and hard work. And during their studies and training here, our graduate students provide most of the research results that makes us proud. And so they're really essential players in the pursuit of our mission. So we strive to continually improve the support of our graduate students. And the support comes from teaching assistantships, grants, and philanthropy, essentially. The teaching assistantships support about a quarter of our students. Grants support most of our students, but funding for science at the federal level fluctuates. And so we're very eager to find sources of funding that are more stable to support our graduate students. And in this context, I want to tell you about an extraordinary opportunity at UCLA right now, that any endowment of between 100,000 and $1 million will be matched 1-to-1 by funds available to the Dean of Physical Sciences. And any endowment in support of graduate students of 250,000 or above will be matched 2-to-1 by funds available to the Chancellor and the Dean. So your gift gets doubled or tripled at the present time. This is a limited opportunity. It's a phenomenal opportunity, and we want to draw your attention to it. Now, I realize that most of us are not in that income bracket that can make these kinds of gifts, but if you believe in our mission of outreach and education, there are other things that you can do to partner with us, and I'm listing some examples here. So we want to improve our outreach activities. We want to have an outreach award to recognize and provide positive reinforcement to our students who are most involved in outreach. We're proud about our instructional demos that really convey concepts in the classroom. I've spoken about funding for graduate students. We also have an extensive field program where students go out in the field and learn about the geology or the geophysics of our planet. We want to improve that program as well. There's opportunities for named seminar series and student awards. So if you're in a position to partner with us, we would love to talk to you. So today's speaker is Dr. Linda Spilker. She's a former graduate student of our department, and she's now at JPL. Linda got a bachelor's and master's in physics from California State University, Fullerton. She obtained a PhD in our department in geophysics and space physics. And she joined the Jet Propulsion Laboratory immediately after obtaining her bachelor's, initially working on the Voyager mission, which provided the first grand tour of the solar system. And she then became a Cassini mission scientist in 1990. And since 2010, she has been the Cassini mission project scientist, a role in which she directs essentially the entire team's scientific investigations. So we're very fortunate to have her. She's ideally placed to give us an overview of this phenomenally successful mission, the Cassini mission at Saturn. We will have a question and answer period after the talk. If you have questions for our speakers, please write them down. Do you have index cards? Did we distribute index cards? Yes, okay. Write them down on index cards, and our student volunteers will collect them at the start of the Q&A. So now I'd like to ask you to please welcome our speaker, Dr. Linda Spilker.
Well, good evening. I've had the privilege to work on the Cassini mission for almost 30 years. And 30 years is the amount of time it takes for Saturn to go around the sun once. So essentially, I've worked on Cassini for one Saturn year. And when I first started on Cassini back in 1988, my oldest daughter, Jennifer, had just started kindergarten. And now she's married, and she has a daughter of her own. And I think, where did those decades go? What an incredible mission with Cassini at Saturn. In fact, Cassini's discoveries have revolutionized our understanding of the planet itself, of the complex ring system, the dynamic moons, and the incredible magnetosphere that surrounds Saturn itself. So what a wonderful opportunity. This is one of my very favorite pictures. This is a solar eclipse picture. And in this case, Saturn is covering up the sun. And just a few times in the mission did we position the Cassini spacecraft such that the sun was covered up and we could take our sensitive cameras and detectors and make this beautiful mosaic of Saturn and all of its rings. So the rays of light are coming through the rings into your eyes. Now, if you look at this picture, you'll notice that there's a ring of light around Saturn itself. The sunlight is being refracted through Saturn's atmosphere. And if you think about it, you're seeing every sunrise and sunset around Saturn at the same time. So truly amazing to look at that. Also, you're looking at the night side of Saturn, and yet there's light falling on the night side. What we see here is the light is reflected light coming from Saturn's rings, lighting up the night side of Saturn itself. There are also additional planets in this view, including the Earth. If you look down here in this corner, can't quite see it, but there's a pale blue dot in that as a picture of our own planet. Now let me tell you a little bit about my story, and in particular, my experiences at UCLA. It turns out I started working at JPL 40 years ago, fresh out of school with a bachelor's in physics, worked on the Voyager mission for about a decade. And during that time, I worked with some of the science teams, both in the infrared and also looking at occultations, watching as a star moved behind the rings of Saturn, Uranus, and Neptune. And I was so intrigued by the structure and the waves in the rings, and I realized to really do what I'd like to do, my own independent research, write proposals, I needed to go back to school and get a PhD. So I applied to UCLA. I wanted to keep working at JPL. I really enjoyed what I was doing with Voyager, and Cassini was looming on the horizon. So I applied and was accepted at UCLA, arrived at UCLA, and started taking classes. Now, I'd been out of school a long time, and so I realized I'm going to have to go back and take tests and work on homework, and so it was kind of an adjustment going back. And I also had grant money, so I could work half-time at JPL, work on my research, and go to school. So I was looking for an advisor, and I was talking one day with Chris Russell. And I was explaining to him my passion for the rings and these wonderful waves. And I wanted to understand and characterize the waves because it tells you about what's happening to the particles, their surface mass density, what's going on in the rings. And so Chris said, well, you know, waves in the rings. He says, the magnetosphere has waves. He says, I'd like to learn about waves in the rings. And I said, great. And so I had my thesis advisor. Another key person in my time at UCLA was William Newman. I took a class from him called Time Series Analysis. And it was so interesting and intriguing. And what I learned from his class, I actually applied to the ring data around Saturn to characterize those waves. Another person I had excellent interactions with was Bill Kalla. He was on my thesis committee, and we talked a lot about orbital dynamics, not only about ring particles, but I took a class from him. And I remember one of his favorite sayings was that if something, say, a comet passes by Jupiter and nothing happens, just wait, that comet would return to the scene of the crime, crossing Jupiter's orbit, and sooner or later might turn into a Shoemaker-Levy 9. Also had a very good friend, a friend going all the way back to my bachelor days, and her name was Candice Hansen. And she and I had gone to undergraduate school together, we'd worked on Voyager together, and we were actually getting our PhDs at UCLA at the same time. So we would carpool. We had to drive in from the Pasadena area, we'd talk about our classes, quiz each other before tests, talk about our jobs, our daughters, our families. And so she was part of that wonderful support system in my time at UCLA. Now, if you look very carefully at those letters, it spells out UCLA. And I have to say, I really got a wonderful education and a wonderful start that led to where I am today, working on the Cassini mission. Well, let's get back to the Cassini mission. And first of all, why do we go and explore the planets anyway? Well, there are some grand science questions that we go to answer. And the first, a very fundamental question, is are we alone in the universe? Has life originated somewhere else besides the Earth? And how did life originate on the planet itself? A second grand science question is, how did the solar system and the Earth within it come to be? What happened to create the solar system? How is it evolving? And where is it headed? And you can see all of the planets here shown in the solar system. Well, this is a view of Saturn. Saturn is 10 times further away from the sun than the Earth and is truly a giant planet. It's a gas giant. It has no solid surface, mostly made up of hydrogen and helium. And if you could turn the Earth into a marble, 764 Earths would fit inside Saturn. Well, let me show you a view of here is the Earth and the Moon and the distance between them to scale. Saturn and its rings would just fit in between the Earth and the Moon. So truly, as the second largest planet in our solar system, a giant planet. This is a view of the Cassini spacecraft on your left. It was provided by NASA, and you can see the people there for scale. And on the right is the Huygens probe, and it was provided by the European Space Agency. And we had a wonderful international collaboration on the Cassini mission. Here's the spacecraft, tell you a little bit about it. That white high-gain antenna is about 13 feet across. We use that antenna to send all of our data back to Earth, to communicate with Cassini, and also for some science. Our radar and also radio science were driven from that antenna. The spacecraft itself is about 22 feet tall, fully fueled. It weighed about 6 tons. And over half that was the fuel Cassini needed, much of it just to slow down, go into orbit around Saturn. You can see a remote sensing pallet that holds the cameras and the spectrometers from the ultraviolet to the infrared, a cosmic dust analyzer, a palette of fields and particles instruments that can sample the electrons and ions and plasma around the spacecraft, 11-meter magnetometer boom, and we have scientists here at UCLA that have worked on that data and helping us understand the magnetic field of the planet. Now you'll notice that Cassini doesn't have any solar panels. Cassini is powered by 3 radioisotope thermoelectric generators and use the decay of plutonium, the heat from that decay, to power the entire spacecraft. And at launch, that was about 700 watts of power. So you can think of 7 100-watt light bulbs to power all of the instruments on board Cassini. You can see we had 2 engines on the bottom. We wanted to be really sure we went into orbit around Saturn, so we had a redundant engine just in case. So this is the machinery of Cassini. But there's a lot more to Cassini than just the machine. And this is my view of the heart and soul of Cassini. And that's the people, the scientists, the engineers, the administrators that work on Cassini and their wallpaper. The people on the Huygens probe are the scientists that worked on the probe data and wrapped around the rest of the spacecraft. And over the decades, we've really grown close, and I consider us a Cassini family. Well, here are the flags of the 19 countries that are involved with Cassini, providing hardware, scientists, other aspects of the mission, and that international collaboration has been wonderful because you pull the ideas from groups of scientists from around the world to create, I think, an even better mission. This is an overview of the Cassini mission shown against the 30-year orbit of Saturn. You can see the seasons of Saturn. We arrived at Saturn, first of all, launched in 1997. Took 7 years to get there. We had 2 flybys of Venus, a flyby of Earth, Jupiter, finally onto Saturn. And each of those flybys was like having additional rocket fuel on board to get us all the way out to Saturn. We arrived about 2 years after northern winter had begun. We had a 4-year prime mission that went extremely well. So NASA funded a 2-year equinox mission, a time when the rings are edge on to the sun. You can think of fall and spring here on the Earth. And then a 7-year solstice mission. And so if you look at Saturn's orbit, Cassini in its 13-year mission has been at Saturn almost 2 seasons. Seasons change very slowly on Saturn. Then the final year of the mission in the green box is basically a brand new mission as we got closer to the planet than ever before for the ring grazing and for the grand finale orbits. Here's another view of the mission, this time in the number of flybys of the different targets. You can see the shapes of the orbits in the very top line. We flew by the giant moon Titan 127 times. And we used Titan not only because it was scientifically interesting, but also to shape the orbits, going from looking down on the poles of Saturn to the equator, to going in and out as we changed the shapes of our orbits. So a very exciting time. You can see the tiny moon Enceladus. We had 3 planned flybys in the prime mission, and the discoveries were so interesting that we flew by Enceladus another 20 times. The other icy satellites, 15 very close flybys coming within less than 1,000 kilometers. In some cases, Enceladus, our closest flyby, was only 25 kilometers away. To talk a little bit about Saturn, here's our views of Saturn through the various seasons, from the beginning to near the end of the mission. And what's wonderful is if you look at Saturn, the shadows on the planet are like a sundial. By looking at the shadows of the rings, you can tell what season it is. We first arrived at Saturn. The ring shadows are in the northern hemisphere. At equinox, the rings were a thin shadow at the equator, and then into the southern hemisphere. We first arrived, what a surprise. That golden-hued atmosphere of Saturn in the northern hemisphere was a beautiful blue. It turns out that with the sunlight gone and the ring shadow falling on the atmosphere, that the haze particles slowly go away, and you can see deeper into the atmosphere and see basically methane coming out. It looks a lot like Neptune or perhaps even Uranus. Here's another view. The shadows have now moved to the south, and you can see that the northern hemisphere has a lot less green and blue in it, and those colors are slowly changing into the southern hemisphere. And you can see giant Titan there with the rings edge on. Well, here's that same view I showed you earlier of Saturn, a view you can only get with a spacecraft. The shadow of the rings going off to the left. And if you look closely, there's a very interesting feature in the northern hemisphere. It's a 6-sided hexagon. It's a jet stream at Saturn. If we blow that up, you can see that it has sides that are very sharp. First discovered by the Voyagers over 35 years ago, still there today. Now we have jet streams on the Earth. You see maps of them in the paper, and they change almost daily. In this case, this giant hexagon, 2 Earth diameters across, is circling right around the North Pole and has been there over the decades. Here's a false color movie. You can see the clouds zipping around. The clouds go very fastest right at the edge of the hexagon. Imagine the clouds racing around like horses on a racetrack. If you look in the center, you'll notice another Cassini discovery. A giant hurricane, 50 times larger than a typical Earth hurricane. This would cover half the continental United States with wind speeds over 4 times an Earth's hurricane. If we blow that up, you can see the sun shining in from the right and the shadows shining on the eye wall in this giant storm. And there's a similar storm at Saturn's south pole. These hurricanes are right at the poles, and over the time of the mission, they didn't change. They stayed in place and just existed there, circling around just right at the pole. We also saw something very amazing. It turns out that about once every 30 years, once every Saturn year, there's a giant storm that forms. This storm was so large that it wrapped around and its head and its tail collided. It lasted about 9 months. It started at the end of 2010, and then it disappeared. Now, in this case, this storm arrived about 10 years early, and luckily for Cassini, it was early, and so we had a chance to observe it. If you look in the near infrared, you can now see that storm, that greenish vortex there. You can see the clouds that it spins off behind it, and a tremendous amount of heat energy is released in this single storm. And some of that heat rises up like a giant thunderstorm. In the far infrared, it looks like a giant cyclops eye looking out for all of the heat that came out of this particular storm. Saturn also has aurora. This is looking at the aurora at the South Pole. They flicker, and they're very similar to the Earth's aurora. The difference is the emissions are coming from hydrogen. And so on Saturn, the true color of the aurora are actually pink, fading to a pale purple. This is a view near the end of the mission of some of the aurora taken in the ultraviolet, and you can see some of them go almost to the pole, which is unusual. Usually the aurora are in a ring, but in this case, some piece of the aurora are going all the way to Saturn's pole at the center. This is a view of Saturn's rings. The rings are made mostly of water ice. They're tiny particles that range in size from about the size of a marble up to houses or even mountain-sized particles. And the rings, as expansive as they are, fitting in between the Earth and the Moon, are very thin, only about 10 feet or less thick, so paper thin in this particular context. Mostly water ice and some non-icy material. And the rings have very simple names, A, B, C, D, D closest to Saturn, E, F, and G. So of the rings that we have named. And the E ring in particular is it's thickest at Enceladus and goes all the way out to the orbit of Titan. And here's another Cassini view of those rings. It looks like the grooves on a phonograph record, tremendous amount of detailed structure. And this is the structure and the waves that I studied when I was here at UCLA. And there are some gaps in the rings. Some of those gaps are actually created by moons that open up the gaps with their gravity. Well, have you ever wondered what happened to your lost luggage? Maybe it's ending up in Saturn's rings. And this is actually from a t-shirt that I have about wondering if this is really what the rings of Saturn are made of. This is a movie of the rings. You're looking at the side that the sun shines on, the lit side. And yes, you can see as Cassini took this series of pictures and created this movie, their moons will fly by every once in a while and the rings will close up. And the thickest, brightest rings that are on the lit side will turn dark. So you can see the thickest, brightest B ring is now dark. The dusty material in the Cassini division is lighting up. You see the A ring and just a hint of the C ring to the very rightmost of the image. And Saturn is all the way to the right. And this is what the unlit side of the rings looks like. So the rings that are brightest on the lit side, the sunlight, they now block the sunlight and look darker on this particular side. Well, we got some of our best views of the rings at Saturn orbit insertion. And here's a view of two of those waves that I studied, something called a spiral density wave that's like wrapping up a spiral galaxy as tightly as possible, and a bending wave. And these were the best views we had ever had of the rings. After we'd slowed down and gone into orbit, we turned our cameras, and as we went out, skimming across the rings, took these pictures. If you blow it up, what we noticed is that in those longer waves, the ring particles were actually squeezed together into clumps. And it turns out that a lot of material in Saturn's rings, the particles stick together, sometimes just temporarily, and form these long clumps. And we nicknamed that structure straw because it kind of reminded us of little bits of straw. Here's an even more incredible view from the end of the mission. This is one of those waves that just seems to go on and on. Many of these waves are created by resonances with the moons in the Saturn systems. In this case, Janus is creating this wave. It's a 2-to-1 resonance, so the place in the rings that goes around exactly 2 times. For Janus going around once, you get a resonance. Imagine pushing someone on a swing at just the right rate, and that's putting energy into the ring. Turns out Janus shares an orbit with Epimetheus, and every 4 years they switch orbits. And we can see that in the waves because you can see there are glitches where the wave pattern looks very regular and it takes like a stutter step. And so we can actually see the history of this wave with time. There's some other fascinating objects called propellers in the rings. These are objects that are not quite big enough to open up a gap, but those little bright arms are a piece of a gap that they're trying to open up. These objects are probably half a mile or a mile in size, and they have really fun names. We named them after aviators, old-time aviators. So you have Earhart, Blériot, Santos Dumont. And there's even a family of propellers in the A-ring. Those little circles are showing little tiny dashes, a whole host of propellers you can only see when you get up really, really close to the rings. One of my very favorite set of images, besides the one I showed you earlier, had to do with looking at the rings at equinox. Here's a view of the rings with their edge onto the sun, and you essentially turn the sun off with respect to the rings. And in this picture, we've had to enhance the left-hand side about 30 times, the right-hand side about 60 times, so you could even see them. And what's unique about this time is with the sun edge onto the rings, anything that sticks up above or below the rings will cast shadows. So here was our chance to probe the 3-dimensional character of the rings. And we saw this incredible picture. This is the outer edge of Saturn's B ring. I show you right here, it's this bright ring, the edge right here. We found all kinds of long shadows. Imagine giant icebergs casting shadows above the rings at equinox. And these objects are probably as much as even 2 miles in size. And they've crowded together at the edge of the A-ring. They can't go any further. And so they grow into basically mountain-sized objects. A good analogy for what you're seeing here is imagine that you're riding in the space shuttle and you're looking down at the pyramids. If you look down around noon, the pyramids are going to blend in with the sand and you won't be able to see them very easily. But if you look at sunrise or near sunrise or sunset, then the shadows will be very long. And the pyramids will cast long shadows. You'll be able to find them. In the same way, we can find the large structures sticking up in Saturn's rings. Here was another fun one. It turns out that there was a bump at the outer edge of the A-ring. And this long bump, about 1,000 kilometers long, was created. You can think of it as one arm of a propeller. And there was an object there that we couldn't quite see, but we could see that structure. And so the person that discovered it nicknamed it Peggy. He thought we were seeing the beginnings of a tiny moon forming. One idea is maybe the moons form out of ring particles and then go away from the rings, and that could explain some of the population of the tiny moons. And he named it Peggy because he discovered it on his mother-in-law's birthday. And so he thought it would be fun to name Peggy after her. Moving on to the icy moons, there are 62 moons orbiting Saturn. Many of them are in the distant reaches of Saturn. They're objects that have been captured by Saturn's gravity. The largest is the giant moon Titan. And just to show you how big Titan is about the size of the planet Mercury. So if Titan had formed anywhere else in the solar system, it would have been a planet in its own right. I'm just going to say a little bit about a couple of the moons. This is Iapetus, big puzzle from Voyager. It has one side as bright as snow, the other as dark as charcoal. With Cassini, we learned that it's dust from the moon Phoebe that's coming in and coating the dark side of Iapetus. And there's a huge ridge of mountains at the equator. Shown here, the ridge, it's about 2,000 kilometers tall. You can see it's old. It's peppered with craters. And it's over 20 kilometers high. In fact, Iapetus kind of looks like a walnut, like someone's taken 2 halves of a walnut and put it together. Here's another tiny moon, Pandora. It's about 50 miles across, and it's coated with ring dust. And it has softened craters. You can even see some of the bright-rimmed crater edge right here. It looks like there's been a landslide that's pulled the material away down into the crater. Another family of tiny moons. Look at these. These have skirts of material around them. These are moons that orbit either in ring gaps or near the rings and have collected around their equators. Remember, the rings are only about 10 feet thick. Collected around their equators, all of the ring dust. And Pan, in fact, some people say kind of looks like a ravioli. Here's a picture of Daphnis orbiting in the Keeler Gap, and it's keeping the gap open and creating these beautiful waves. Imagine like a motorboat wake behind it, creating a beautiful wave along the edge of the ring. Moving on to Titan, this was Voyager's view of Titan. A haze-enshrouded world. Think of Los Angeles smog on a bad day, organic chemicals and smog. And so one of the reasons we went back is after the Voyager flybys of Saturn that we couldn't see through to the surface of Titan. So one of the key goals was to go with a probe, parachute down through the atmosphere and look for the first time and unveil the surface of Titan. So with the European Belt Huygens probe, here we are, coming in the upper left. The heat shield slowed the probe down enough to deploy a parachute. We were under that parachute, and it turns out we had to switch to a smaller parachute to make sure we got to the surface before the batteries wore out. Took about 2.5 hours to fall all the way to the surface of Titan. And Huygens became the first man-made object to land on a moon this far away from the sun. You can see here the images coming down. We measured the pressures and the temperatures. You can see the images as the probe went down, it was circling and taking pictures. First, you can only see the haze. Then you start to see evidence of what looks like mountains. And finally, landing on the surface, we landed in an area, in that golden region, we could see rounded icy pebbles. And that told us that fluid flowed on the surface of Titan. There's a footprint you can see from the lunar landing, just to give you perspective. And then on the far right, you can see we found river channels. It's so interesting. It's cold on Titan, but it turns out that methane plays the role on Titan that water plays here on the Earth. You can have methane clouds, methane rain. Methane can flow through river channels, round icy pebbles, and actually fill the lakes and seas. Here's a view of Titan's North Polar region. We carried some near-infrared filters so we could see through the haze. You can see those dark blobs up there, some of the seas on Titan. And we wondered, did those seas contain liquid or some kind of a goo? We didn't know. But then we saw this signature. It's called a specular reflection. Light hits the surface of a liquid at just the right angle. It bounces off and creates that bright spot. If you've ever been on an airplane on the side away from the sun, you might be looking down and notice every once in a while a stream or there might be a bright spot on a lake. Those are specular reflections. So we knew for the first time, Titan had liquid methane seas. We carried the radar instrument and got exquisitely detailed views. You can see the river channels and streams and rivulets coming into this sea, Ligeia Mare. Ligeia Mare is about 50% larger than the Great Lakes on the Earth. It's about the same depth, about 500 feet deep. And if you added up all of the hydrocarbons on Titan, it turns out that Titan has about 100 times more hydrocarbons than the Earth. So just imagine if we could only build a pipeline all the way to Titan, our problems would be solved. Well, here's an example of some of Titan's weather. These clouds formed as it got to be summer in the North Polar region. If you look at the picture on the bottom right, you can see that arrow-shaped orange methane cloud, and that yellow spot is a specular reflection from one of the Titan seas. Well, here's Enceladus. Enceladus is 1/10 the size of Titan, so a much smaller moon. It's about 300 miles across. When you look at Enceladus, you notice, Enceladus has places that really don't have any craters at all. Its surface is very bright white. Its surface looks very young. What could be going on? And with Cassini, we noticed that there were 4 features, tiger stripes we call them, at the South Pole. And that was the key to Enceladus. It turns out that when we looked with our magnetometer on one of the first 2 flybys of Enceladus, it looked like Enceladus had an atmosphere standing off kind of like a comet tail. And so the magnetometer team said, we need to go closer. So on the third flyby, we went within 175 kilometers of the surface, and we made some amazing findings. We found that there was excess heat coming out of the tiger stripes. It was 100 degrees warmer at the South Pole than it should have been if Enceladus had just been in equilibrium temperature. Here's one of those tiger stripes. They're about 130 kilometers long, 2 kilometers across, and about 100 meters tall on the edges, and about 500 meters deep. And so we looked at these fractures, and you can see on one edge here, it looks like almost like it has frost on the edge. It turns out it probably did, that there were geysers of liquid water and icy particles filled with organics and carbon dioxide and ammonia streaming out of those 4 tiger stripes. In fact, there are over 100 individual jets that we discovered with Cassini. And we were lucky with Cassini, we actually retargeted and flew through that material 7 times, tasting and sniffing and figuring out the composition about what was going on with Enceladus. And when you have 13 years, it gives you time to work on this most intriguing puzzle. Here's another view of those jets coming out from Enceladus, shooting out into space. We think that perhaps it's kind of like champagne. There are carbon dioxide bubbles, and that perhaps lifts it up, and the bubbles expand, expel the material into space. Now here's another Enceladus. This is a fountain at Versailles. It's very different from the typical fountains that you would see. And this is Enceladus. He'd gotten himself into a bit of trouble, and here he is, and he has this fountain of water, this fountain built in 1670, coming out of Enceladus. And who would have guessed that this was close to the truth? The moon Enceladus actually does have geysers of water shooting out. Some of that material escapes into space. Most of it falls back to the surface, fills in the craters, and makes the surface bright white and fresh. But some of the very tiniest little particles, about the size of smoke particles, escape into space and create the E-ring. And you can see the wispy fingers, that dark dot is Enceladus. You can see the bright plume coming out from the bottom, and that wispy tendrils creating Saturn's E-ring. As we studied Enceladus further, we found out not only did it have liquid water underneath the tiger stripes, but it had a global ocean completely encircling a rocky core. That ocean was salty, and that ocean also had hydrothermal vents on the seafloor, that we saw an excess of hydrogen and other particles that could only grow in water close to the boiling point. Now we know if you look at the hydrothermal vents on the Earth, in the places where the seafloor is spreading, the water goes down, gets heated up inside the rocky crust, picks up minerals, and when it comes out, it loses those minerals, and it looks like smoke underwater. These hydrothermal vents are so deep, there's no sunlight. And yet if you look, no sunlight going through them. And so we're looking and wondering, could you have similar activity going on Enceladus? You've got a global salty ocean, long-lived organics, heat energy, and hydrothermal vents. And if you look, and we're getting free samples because we can fly through with Cassini. And if you look near the Earth's hydrothermal vents, it's teeming with life. So we wonder, could there be life in the ocean of Enceladus, 10 times further from the sun than the Earth? And it's very intriguing to think about. But Cassini doesn't carry instruments to look for life. So it will take a mission to go back and see if there's life possibly there on Enceladus. I just want to finish up with a few words about Cassini's grand finale and how hard it is to say goodbye to a spacecraft. Now, for the final set of 22 orbits, starting the end of April, we actually were diving in between Saturn and the rings, flying in a place that no spacecraft has flown before, and getting closer to the planet and the rings, and just so intriguing in this particular region. But Cassini, we went into this set of orbits because Cassini was running out of fuel. And we not only got great science, but we had an end planned that would take the spacecraft and end it in a way that would be appropriate. So why would you crash a perfectly healthy spacecraft with working instruments into Saturn? Well, you're running out of fuel, and as I've talked about, there are 2 worlds that we need to protect. And those worlds are Enceladus with its global ocean, and Titan with its liquid methane seas, And it too has a liquid water ocean underneath its icy crust. You know, astrobiologists wonder, could you have really very different, unusual life forming in a methane sea? So with Cassini, the end was to plunge into Saturn, which we did on September 15th. And that marked the end of the Cassini mission. Now, if you could ride along with Cassini, imagine holding on to that white high-gain antenna. What would it feel like to ride through one of those orbits? Well, here's a view compressing about 2 hours of time into 15 seconds. There you go, diving through the gap on out in your orbit, and you can see the sun shining off there. 6.5 days later, you come back, and you do it again. The rings spread out before you, and then whoosh, you're gone, and you're going through that gap over and over again. I kind of imagine it being like standing on the deck of the Enterprise and actually being able to fly through the rings of Saturn. And so we were able to do that over and over again. And just a couple of the highlights from that time. We're actually able to get this movie. You can see the red dot moving down Saturn. We got some of our closest views ever of the planet itself, seeing all kinds of amazing and incredible cloud features, creating something we called a noodle, because it kind of looked like a noodle as we flew down. And here's did that twice. Here's a couple of noodles. The first one was in the clear filter, and then we looked with methane to look at different places in the clouds. And here's just a view of some of those clouds. And there was such excitement. It was on April 26th for that first flyby. I remember that date because it was my birthday, and I thought, wow, Cassini survived, and that's a great birthday present. We made it through. The ring particles didn't hurt us. But one of the scientists there, Andy Ingersoll, he looked at this picture, and he was standing there doing instant science, and that's so much fun to do. And he said, you know, I've never seen anything like this in my life. And he was just smiling from ear to ear, because that's what scientists like, to have puzzles and things that they can't explain right off the bat. And then here was a view of the rings. To me, this is like having the rings right in front of your nose. It felt like you were that close to look at the rings. And so here's one of those ringlets, one of those plateaus spread out. And you can see this incredible streaky structure. You're almost seeing the individual clumps in the rings. And we have all kinds of creative names. There's straw and streaky structure and clumpy and wispy, and all these creative names to describe what we see. And we were so fascinated to see that here's clumpy, here's nothing exciting, lots of streaky texture, and just incredible. And we're still puzzling and trying to figure out, how can the rings change on such short scales? What's going on? So give us another couple years or 10 years, and we'll have a much better answer for you. Well, with that, I'd like to then just, let's see. Oh, also another thing that we did with cameras is to turn and look at the rings from the inside out. And you can see in this graphic here, here's Cassini looking outward from the rings, and there's the series of pictures we took as the rings close, and then we see just a little bit of the unlit side. So we call this looking at the rings from the inside out, and a chance to have views that we haven't ever had a chance to see before. Well, beside looking at Saturn and the rings, then there's the space in between. Also, we had a chance with our magnetic field instrument and our gravity measurements to look at the inside of Saturn, to try and understand what's going on inside. We had hoped with our magnetometer data to get the length of a day for the inside of Saturn, but it turns out that that's not so easy to do, so we're still working on it. Saturn's gravity field doesn't match our models. We had some models, and some of its higher order terms, what we call higher order harmonics, are different from what we expected. One thing about scientists is they love it when their models break and the answers don't work anymore, because then they get to start over and come up with a new model. And so there's lots of very, very happy scientists. We're also planning on getting the mass of the rings, and that's important because if the rings are less massive than we expect, they might be young, maybe only 100, 200 million years old. They're trending that way, but so far our error bars are really large, so we don't have a definitive answer for that yet. Well, one of the last pictures that we took with Cassini before we turned and played all the data back to Earth was to look at Cassini's final resting place. What did that place look like where Cassini would have its fiery final plunge? And so you see on the left, this is an image taken near infrared by the visual and infrared mapping spectrometer. It's at 5 microns. It's the heat energy coming out. And the dark spots are places where the clouds that are higher up and cooler block that energy. And that little white oval is the region where Cassini plunged. Then on the right is a visible image. And you're looking at Saturn's night side. But once again, the light from the rings is lighting up Saturn. And so you can see what that atmosphere might look like. Well, as we got closer to the end, we were traveling at 74,000 miles an hour. And this shows the little time ticks every 10 seconds until the final loss of signal at that region in the atmosphere that I showed you earlier. And what we saw as we sat watching the screens, we saw the radio signal. So here's the radio signal. That little peak, you can think of that as Cassini's heartbeat or lifeline to the spacecraft. So it'll cycle through again. We saw a strong signal. The top is called X band. There's a strong signal that pops up. It slowly disappears. Then the S band signal disappears. And then the mission was over. And at first there was silence in the room and people started to applaud. And then people started to hug each other. And it was a very wonderful moment to share together as a family. And in that top picture, you can see the project manager, Earl Mays, the spacecraft manager, Julie Webster, and the bottom, some more of my Cassini colleagues, with that final loss of signal. Now, here's a view of, we tried to get together at JPL, all of the alumni that have worked on Cassini. And so this is just congratulations to the team. We didn't get everybody, and this is just the people that were at JPL. But what an incredible, spectacular mission. And UCLA has played a very large role with its scientists and also with some engineers that got their degrees here at UCLA in being part of this wonderful, incredible mission. And for me and for the Cassini family, this mission was really a Disneyland e-ticket ride, without a doubt. And now what I want to do is I want to show you what was shown right after the plunge. A group of people had put together this very nice video, just 2.5 minutes long, of some of the images that we took of Saturn with its final goodbye. Well, with Cassini, we truly had a rare opportunity to unveil the wonders of Saturn, and we seized it. And personally, I think we need to go back. Thank you.
If I may ask our panelists to join us on stage, and also now might be a good time to write down your questions if you have some questions for our speaker.
In particular order.
All right, so let me introduce the panelists. Immediately to my left is Sean Falk. He's a UCLA Earth, Planetary, and Space Sciences graduate student. So he's currently filling the shoes that Linda used to fill in our department. Next to him is Professor Chris Russell. We've heard about Chris in Linda's presentation. He was Linda's thesis advisor. Linda. And then Krishan Khurana, he's a researcher in our department and was involved in the Cassini mission. So I'd like to start maybe with Linda. Can you identify a favorite memory of your time at UCLA?
I have a lot of favorite memories about being at UCLA. I enjoyed talking with the students there. But I think one unique thing stood out. One of the first classes I took at UCLA, I took with Dave Page. It was an Oceans and Atmospheres class. And I'll never forget that during the final, all of a sudden, partway through the final, Dave said, the pizza's here. And he had ordered pizza for the class during the final. And so we took a pause, we ate some pizza, and went back to our final. And I have to say, that's the only time I've ever had pizza during a final.
That's a fun one. So Chris, what was it like to work with Linda when she was a graduate student?
Well, it was a very interesting experience because what I liked about Linda is she brought something with her, which was the ring study, which she wanted to do for her thesis. And I didn't know anything about rings, so she was training me, and that was quite useful. And now I got involved in the Cassini project eventually, and I understood a lot of those things that Linda had studied as part of her thesis. So she taught me during that period of time.
All right. Well, maybe we can ask the student perspective. What was it like to work with Professor Russell?
Well, I have to say it was quite interesting. He was quite a taskmaster. And one story I can tell, I remember when it got time for taking my qualifying oral exam, it was not too long before the Neptune flyby, and he came to me and said, I think it's time for you to take your exam. I said, I can't. I haven't studied enough, and the flyby's coming up. And he said, yes, you can. He said, you can do this, and you can study for it. And he says, you'll enjoy the Neptune flyby a whole lot more if you get this exam out of the way. And he said, and by the way, you'll thank me. And he was right. I did. I took the exam, passed, and I went back and I said, thanks, Chris. And it worked out.
So, Sean, I want to talk about your recent article. You just had an article published in Nature Geoscience. It was based in part on Cassini data. So can you tell us about your work and the kinds of questions you're trying to answer as part of your research?
Yeah, definitely. So I study the climate of Titan, which Linda talked about a little bit. So this is the world that she showed these awesome pictures of the lakes and seas and these flowing river channels, except because it's so cold, it's not liquid water, but liquid methane. And so what we do in my group with Jonathan Mitchell is we use climate models from Earth, but adapted to Titan to look at the weather and the climate on Titan. And that's how we get an understanding of what's going on in the Titan system. And so the way that we use Cassini data is that in order to improve our model and to make sure our model is doing the right things, is reproducing the natural system of Titan, we compare what we get in our model to the clouds that we see from Cassini and the surface features that Linda showed, like where the liquid methane is, where the river channels are. And so yeah, we use a lot of the radar data, the images. It's been a lot of fun looking at this sort of Earth-like world, but in a totally different context.
And some of these storms are quite spectacular.
Yeah,
right?
yeah. So what we found recently is that some of these storms can get basically as intense as what we've seen recently in North America. Some of these, like Hurricane Harvey, storms of that order are happening on Titan pretty much once in a millennium or so. And so these are storms that can rain down like a meter of methane at a time. And so it's quite impressive. And we can learn a lot about Titan, but also about Earth's climate by comparing the two.
That's great. Christian, I wanted to ask how you got involved with the Cassini project.
I think it was about 20 years ago, almost in October, this kind of time. Cassini had just been launched, and Chris Russell was looking for someone who can help him plan observations. And I had been working with Galileo at that time, doing the type of things we wanted to do at Saturn. And so he asked me if I'd be working with him, and that's how I got into it. But you know, the question can also be asked in another way. How does one get into such a fantastic mission? And my suggestion is get on the ground floor, help plan those missions, help define the science so that when one day the mission becomes a success, it launches, you're there in the ground floor.
I have a similar question for Linda. Do you have a piece of advice to give to our students?
I think I would agree with Krishan completely. You know, if you can get involved, maybe a summer internship, if you know some scientists, if you have a chance to go to a scientific conference, that's a great place to network with scientists, to, as Christian said, get in on the ground floor and then find something you like and get involved and become part of the mission in that way.
So Professor Russell is currently leading the Dawn mission, and he's the principal investigator on that mission, right? And I wanted to ask Chris about the difference between being a principal investigator on this class of mission and a project scientist role, as Linda is on the Cassini mission.
Well, let's talk about principal investigator, the phrase first. The principal means that you are the one where the buck stops for that particular investigation. So if you could be a principal investigator of a particular instrument, let's say on Cassini, or in the case of Dawn, you can be the principal investigator of the whole mission. What NASA did in 1992 was to come up with a new concept of managing its missions. And that is to put a principal investigator in charge of the entire project, so that he gets to hire or fire the project manager, for example. In Linda's situation, she really works for the project manager. You can't go out and say, I don't like Ed, you know. Get rid of him, please. But I've had to do that, actually, on Dawn, that I got working with a particular project manager who didn't wasn't working effectively, in my opinion. And it took me a little time, but I was able to change the management of my project so that it worked more effectively. We need both types of people. We need the project managers, we need the project scientists, and we have a bunch of investigators leading individual investigations. But the basic structure is different in one mission that's PI class, as they call them, and one that is a much grander type of class like Cassini is. But they both function, they both have a role in our program. And I, having led the Dawn project, I really believe in that concept, and I think that we should, for the medium and small class missions, do it that way. For the large, for a mission as large as Cassini, I don't think I want to go there and devote all my time to management and not do a little bit of science.
So I'm trying to summarize here. The difference is that a principal investigator, she could fire people under her, and
Yes,
a principal,
you could.
a project scientist might not be able to.
No.
All right.
Another way to look at it is a project scientist doesn't have quite the administrative overhead to have to worry about all of the ins and outs of the project. So I kind of think about you have time to really maybe enjoy what you're doing.
And so you talked about the small class, the medium class, and then I guess the flagship type missions like Cassini. The next one will be the Europa mission, the Clipper mission. That will also be a project scientist. Is that correct?
That's correct.
Yeah.
Yeah. In sort of the flagship model
Right.
for that mission too.
All right. So thank you. I want to come back to the science. Christian, we talked about the grand finale phase of the mission, and where the spacecraft went very close to the planet. Can you tell us what we learned about the magnetic field of Saturn during that phase?
Yeah, so Saturn is a large gas giant, and we know that all the 4 gas giants we have in the solar system have pretty strong magnetic fields. And each of those magnetic fields is unique. And one of the great mysteries about Saturn's magnetic field is it's completely axisymmetric. You think of magnetic fields as field lines coming from one end of the planet and returning to the other. Imagine you are stationary in space floating above Saturn, and Saturn is rotating under you. As Saturn rotates and the magnetic field rotates with it, you will not see any change in the magnetic field. Every field line that comes and strikes you would be identical to the one previous one. It's that axisymmetric, and that's a big puzzle, and that's what we try to quantify. How axisymmetric is Saturn's magnetic field? The answer is as much to the accuracy we can measure the magnetic field is axisymmetric. It's a big puzzle. Dynamo theorists, the people who try to come up with models of what creates these magnetic fields, are baffled and happy. There's work for them for coming decades. How does Saturn make such an axisymmetric magnetic field? So that was one thing. The other one, just looking at the same magnetic field, we can map it to its complexity, how strong it is and how it changes with latitude of Saturn. And what we found was that there is a deficit of magnetic field near the poles. And it turns out it was expected, and it is telling us about an internal core, a rocky core inside, which actually stops Saturn from making a strong magnetic field in the polar region. And the deficit is telling us there's a core, roughly the quarter the size of Saturn, present inside. And we can see that in our magnetic field observations.
Did you mean the size of Earth?
How big is the core?
A quarter the size of
A
Saturn.
quarter.
Yeah,
A quarter the size, okay.
Yeah. the size of
That's
Saturn.
huge.
It's huge, yeah. It's much bigger than we had anticipated.
Another surprise. I like it.
Another big surprise. And then finally, one more thing we discovered was the magnetic fields are acting like brakes on the atmosphere of Saturn. So imagine a free line coming from one hemisphere going into the other. The two ends may not be moving at the same speed because of atmospheric winds. And the magnetic field then tries to apply a magnetic braking to the two sides to make them move at the same speed. It's a well-known phenomenon, it's called magneto braking, and it's creating that kind of braking and heating up the upper atmosphere. We saw, there was yet another puzzle. The ionosphere, which is the uppermost part of the atmosphere of a planet, of Saturn is very hot, at least by 70 to 80 degrees hotter than we were expecting. Finally, we know the answer. What's creating it is the magneto braking. Same way, when you brake, your cars apply brakes, it heats up. Saturn is getting heated up.
So on top of the core that you just described, and I saw in a picture in Linda's talk of the interior structure, that's where the metallic hydrogen is, Linda. Can you tell us about
Right.
that state of matter?
Above the rocky core, there's metallic hydrogen, and it turns out molecular hydrogen gets compressed at about 1 million atmospheres down, gets compressed into metallic hydrogen, where it's actually a current can flow. And we think that's where the magnetic field comes from.
That's right. So to be able to create a dynamo field, you require strong currents. Strong currents flow in strong conductors. And hydrogen under high pressure becomes metallic. It's a real metal, and as a result, it's a liquid, and it can flow. It's a liquid metal, and as a result, it can create strong magnetic fields. Saturn has the second strongest magnetic field in the solar system after Jupiter.
It's fascinating. Chris, there's a big puzzle about the rotation of Saturn that Linda alluded to. Can you tell us a little bit more about it?
Well, that when you look down at Saturn, you can see the clouds moving, and so you know how fast they rotate, but you don't see the interior of the planet. That's invisible to you. And so we often use the magnetic field for a planet. For example, on Jupiter, the magnetic field is tilted with respect to the rotation axis, and as it moves around, we can see different radio signals from the planet, and we can time the rotation of the interior, because the interior is determining the magnetic field. So we know the rotation rate of Jupiter, even though it's a bigger planet than Saturn and more mysterious in many ways, because the magnetic field has structure to it and that we can follow the interior motion. We're totally blind for Saturn because of its perfect symmetry in rotation.
All right. Christian, one more question about the field of Enceladus. So you studied it. Can you tell us maybe in 1 minute or two what you found about Enceladus?
So Linda actually alluded to that. So Enceladus has a giant plume. It's being shooting up to about 100 kilometers up from the surface. It can do that because Enceladus is a small body, its gravity is pretty weak. So that's not a problem. But we didn't know about it. And it was actually the magnetometer which discovered that plume. And the way that works is a plume is water vapor. It ionizes once it comes out of, once it free floats in space. And ionic material is conducting. And it can then interact with the magnetic field. The magnetic field gets pushed against this plume it cannot flow through this plume. The plume acts like an obstacle. And we saw that in our data. But what was mysterious to us was the obstacle wasn't centered at Enceladus, it was centered below it. And so just by looking at the magnetic field, we said there's something mysterious about a dynamic atmosphere which is present in the southern hemisphere of Titan. That's where we should be sending our next flyby of Cassini. We did that, and we took lots of pictures, and we saw the plume. So one can actually use magnetometer for dowsing of water. That's what
Good enough.
Sean, I want to ask, why did you decide to come to UCLA?
Yeah, I guess other than the weather. I've always been, I knew I was interested in planetary climate and planetary atmospheres, and something that struck me about UCLA was sort of the interdisciplinary nature of the department that we have here, and that basically across the hall, you have people working on Enceladus and icy satellites, and then also people working on Mars, and then of course people working on Earth. And so putting that all together, you can learn a lot of really cool, interesting things. And I think comparative planetology, or comparing, specifically looking at planets next to each other and looking at similarities and differences, is something that's really interesting and a way to learn a lot about a planet, and especially learn a lot about Earth, I think. And so that's always something that's struck me about UCLA and what I've tried to do, I think. And then also it's really close to, we talked about this a little bit before, Linda, but it's really close to JPL and Caltech, and so that offers a lot of opportunities for collaboration. And I've actually been lucky enough to work with a professor from Caltech on certain things. So yeah, it's been really great.
And you seem to be interested in education and public outreach. Can you tell us a little bit about what you do?
Yeah, definitely. I think that's probably half the fun of science, I think, is to sort of see other people interested and teach other people science. And so I think it's really important to get people to care about things that they might not ever care about, and especially going out into other schools. What we've been doing here, this department's given me a lot of opportunities to go to these underserved communities and go out to these schools and demonstrate science and get kids interested. And so what I've been doing recently is, as part of a group started here in this department, some postdocs in my research group, Spencer Hill and Juan Laura, and then also Professor John Arnaud, is we've been building these rotating tanks that we could send to students, and they're actually simple enough. They're made out of Legos. They're simple enough for kids themselves to build themselves. And on those rotating tanks, you could put like a tank of water and then spin it around, and then you can learn a lot about fluid dynamics in these very simple demonstrations. So yeah, it's been a lot of fun and really rewarding.
That's great. I'd like to get the audience questions, if I could. And in the meantime, I'll ask Linda, what was your biggest challenge as a project scientist?
Well, I think it comes down to working with a big group of scientists, each that all have their own priorities and different desires. And it's kind of like herding cats. It's not easy to herd cats. And probably the biggest challenge was for that very end of the mission with just 22 orbits. Those 22 orbits, it seemed like a lot at first, but each team wanted to do so much science, we could have used 44 orbits. And so it was carefully crafting and planning the very best science. And we'd have these bitter discussions and debates, go off and have lunch together, and come back and start all over again. So I think getting everyone to agree, and I think once everyone is equally unhappy, you've accomplished your goal.
And it's not just herding cats, it's herding very intelligent, nasty cats.
All right, we got lots of questions here, so I'll try to get through them. Sean, have you found weather phenomena on Titan that we do not have on Earth?
So the way that we look at weather is through our models. We've only been able to observe weather on Titan for one Titan year. Essentially, one Titan year is the same as a Saturn year, which is 30 Earth years. So nothing that we've seen, at least to my knowledge, has been something that we haven't also observed on Earth. And everything that comes from our models is already based off of physics, of the Earth. So it's things that that are familiar to us from Earth. one of the interesting things that we found in this study recently is that these really intense storm events on Titan also produce similar surface features on Titan that are produced on Earth. So these surface features are these sedimentary deposits called alluvial fans that are, when you have very intense storms that transports the sediment and that produces a cone-shaped sort of feature that you can see on the Earth, very common in deserts on Earth. And we see these same features on Titan. So that's really interesting that we have this correlation between intense storms on Titan and these surface features on Titan as well. So it's another example of them being similar.
Thank you. I have a few questions that are similar, including a question from Quinn, who's 8 years old. When will NASA send a probe to explore life on the 2 moons with oceans? And he says you should send that mission.
I agree. I heartily agree. It turns out NASA has a New Frontiers program, and part of that program includes missions to go back to Enceladus, Titan, and even a Saturn probe. So 5 of the 12 missions are focused on Saturn. So we'll hear in December. I'm actually part of one of those proposal teams. It's called ELF, Enceladus Life Finder. So I certainly would like to go back with a mission to Enceladus to further explore this question of the habitability of this interesting moon. So perhaps as early as December, we'll hear the 3 to 4 missions that NASA will pick for further study. In a year or so, they'll down select to one, and I hope it's ELF.
All right. Explain the remarkable thinness of the rings of Saturn. You showed some images, but it truly is remarkable.
Indeed it is. It turns out that Saturn is very oblate, very egg-shaped, and has a very high factor called J2. And just Saturn's oblateness, if the ring particle tries to go a little bit north or a little bit south, it very quickly is put back into the plane of the rings and is maintained there. The rings are what's known, for the scientists here, a cold classical disk, and the particles are kept very, very close to the ring plane. And it was really amazing. With Voyager, we thought maybe 100 meters. With Cassini data, it was shrunk down to perhaps as little as maybe 10 meters, and now perhaps even a few meters, only a few feet thick. It's just amazing. As thick as the biggest particles.
Why do rings form so dramatically around Saturn, and why don't the inner planets have rings? That's a great
The
question.
inner planets are much smaller than the outer planets, and so we think that has something to do with it. In the case, it turns out that the 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, all have rings. Saturn's rings just happen to be the most notable and easily viewed through a telescope. In the case of but now we're finding, though, with small bodies, maybe it's not quite so easy because there's this object out there called Chariklo, and it's very small. It's kind of more like an asteroid size than a planet size, and it has 2 rings of its own. So we might have to reopen and relook at that question.
I will also add to that, the ice particles, say for example around Earth or Mercury, will evaporate. So if there could be a ring, it would not be that of ice. There could be a dust ring, certainly. But again, the bodies are just too small to support rings.
Except for Chariklo.
That's all.
Somebody's asking about the tidal process on Titan or Enceladus. So this is a process where the moons get deformed and maybe some heat gets released, which is called this tidal heating. And the question is, do we have any evidence for tidal heating on Titan or Enceladus?
Well, in the case of Enceladus, its orbit is not quite a perfect circle. It's in resonance with another moon, and that eccentricity, we think, actually sometimes it's closer to Saturn, slightly further away, and that causes sort of a flexing. Imagine squeezing on a rubber ball over and over, and that rubber ball would heat up. In the same way, we think that tidal flexing contributes to the ocean that we see on Enceladus. Titan, on the other hand, I think has a pretty small eccentricity. I don't think we've seen evidence for the same kind of tidal flexing on Titan that we've seen as a possibility on Enceladus. I don't know, Christian, you want to comment?
So there are other sources of heat. There's always radioactive material in planets, and so that's another source of heat. But just the size of a body, if you have a body the size of Titan and you want to cool it down so that it's completely solid, even though at one time it started as a liquid water body most likely, It will take pretty long time, and some estimates say as long as the solar system. It's about 4.5 billion years old, and it's quite possible that the big bodies like Titan, like Ganymede, which is a moon of Jupiter, they just do not freeze out in that time. So that could be their other reason for the ocean inside Titan. But for Enceladus, yes, you will need a current source of heat. Tides are the most obvious one. There could have been a collision with Enceladus by another body, say a few tens of million years ago, and maybe there's some leftover heat that keeps the interior of Enceladus molten.
Different kind of question. Who was Cassini and why the name? I like it.
Turns out Cassini was an astronomer, and he discovered, he had a very good telescope, and he discovered the gap in the rings of Saturn between the A ring and the B ring. It was named the Cassini division after him. And so we were looking for names of the missions. The mission Cassini got its name. In the case of Huygens, Huygens was a Dutch scientist who discovered Titan. And so it seemed appropriate to name the probe going down to Titan's surface after the discoverer of Titan.
So it wasn't Oleg Cassini like he thought?
No,
Yeah.
no.
Oleg Cassini tried to sue the Cassini project for taking his name.
So it's true. We had to point out to them gently that there was another Cassini, and that he really, that the name really came from the scientist.
What are the constraints on the age of the rings? A very interesting question, planetary science.
One of the main constraints is the mass of the rings. There's some thought that the rings are massive. You take all the ring particles and scoop them up, you get about the size of the satellite Mimas, which is about the size of Enceladus. If the rings are much more massive, say 10 Mimas masses, maybe they could have formed at the same time as Saturn 4.5 billion years ago, and then the micrometeorites that hit them and erode them, they could have lasted till the present day. They're much less massive than a Mimas mass, and it points to rings that are young. Perhaps a comet or an asteroid or something got too close to Saturn. Saturn's gravity literally ripped it to shreds, and those bits went on to form the ring. And I think it's possible, perhaps maybe the individual rings might represent individual bodies, perhaps, and it'd be different ages around Saturn. There are hints that there's slightly different compositions, slightly different colors. And so the rings are headed towards a young age, and perhaps one or more bodies that were broken apart to form the rings. And perhaps when you look at the rings in the solar system, Saturn has the biggest, brightest rings. Maybe as you go to Uranus and Neptune, maybe those are older ring systems that have had a chance to erode away into much less massive rings.
And was there any danger of particles in Saturn's rings damaging the Cassini spacecraft? And how fast was Cassini traveling on average?
Right, the Cassini spacecraft was going 74,000 miles per hour through that gap. And on the very first orbit, we didn't know for sure exactly what the particle environment would be in between the rings and the planet. We had simple models that said, okay, if you just extrapolate what we think we know, there might be particles traveling that fast that could damage Cassini. So in our very first orbit, we turned the high-gain antenna like a giant shield, a giant white shield, pointed down in the direction of the particles coming in. And then we used, actually, one of the instruments on Cassini, the radio and plasma wave spectrometer. Particles hit their little antennas, then they would make a signal. And we'd done this before, crossing through the E-ring, we got signals. Every time a particle vaporized on these long antennas, we'd see a signal. We fly through this region, we see nothing. It's quiet. It's like we're all, whoa, this is great news for Cassini, but what happened to the ring particles? It turns out that they were there, but they're tiny, tiny, tiny nanograins, literally the size of smoke particles. They're so tiny, when they hit the antennas, they vaporized, but they weren't big enough to make a signal. So it was great news for Cassini. This region was full of nothing but tiny, itty-bitty bits of particles. Great news for ring scientists. What happened to the ring particles that should have been there? So we were safe. We were very safe. In fact, a future mission might want to fly through that gap to slow down and do a mission at Saturn, because it really is very safe in that region.
All right. Question with more of an engineering bend. What were some of the biggest engineering challenges in making or designing Cassini?
Well, some of the engineering challenges are actually to go all the way out to Saturn and actually have to plan a mission, to get the power supply right, to pick out the kinds of instruments that you would need to do the science that you need to do. The initial Cassini spacecraft looked very different. We actually had instead of having these sleek Cassini spacecraft with the instruments bolted on, we actually had two platforms, one for the remote sensing that could turn around and another turntable. And it turns out that these moving parts are expensive to space qualify. So as we had to cut down on our budget, we said, let's keep all the science instruments, take off the moving parts, and just bolt everybody onto the Cassini spacecraft. And so it was a challenge because the instruments were picked. They figured they could move around a lot, and now they had to get bolted on and redesigned slightly to be on this new spacecraft.
And here's
So it made management of the project a little bit more difficult.
It made management and actually flying, because you had to turn now the whole spacecraft every time you wanted to point. And you had to get better at sharing. So if you were
Yeah.
taking pictures, you couldn't be taking radio data or different data. So you had to get better at sharing.
I think we'll wrap it up soon. Unfortunately, we won't be able to get through all the questions, but I encourage you to come and continue to talk to our speaker or panelists. Why are almost all of the planets named after Greek characters?
I think that was a decision that was actually made long ago, long before NASA.
Maybe by the Greeks. And then finally, what surprised you the most from the Cassini mission?
I think the biggest surprise was probably Enceladus, to find this world. It was so small that everything told us it should have been frozen solid, a giant frozen ice cube, like we expected for the other moons, and to find a liquid water ocean, active geysers on a moon that small. That was certainly the very biggest surprise.
All right. Well, thanks again. Please join me in thanking our panelists. And feel free to come and ask additional questions to our speakers. Thank you all for coming.